Okay, so on the first one, just ask you to fill in the table here. Haven't seen that yet. And so I've given you the frequencies. If you sum those up, that's 50. So the relative frequencies will just be each number divided by 50. So that's 0.12, 0.22, 0.34, 0.18, and 0.14. Okay. So I just added those in. And then for the cumulative frequencies, the less than 50, there aren't any in there. Then less than 60, there are going to be 6. That's here. Less than 70, it'll be that 6 and another 11, 17, plus another 17, 34, plus another 9, plus another 7. And of course, this and this will always equal. And if you add these up, that's going to be 1, always. And then to get the cumulative relative frequency, we'll divide each of these by 50. Okay. And again, you'll end up with 1 at the end. Okay, so the first question now, or the next question says, which class contains the first quartile? So remember, the quartile is 25% of the values below this point. Okay? So if we go over here to the cumulative relative frequency distribution, 0.12 of the data are less than 60. 0.34, so from there to there, somewhere in there is 0.25. Okay? So that's the first quartile, and so it'll be in this class. If I asked you where the median was, the next one is 0.68, so the 50th percentile would be somewhere in that 70 to 80. Okay? So I'm just using these cumulative relative frequencies, and it has to be in, we've got, for the quartile, first quartile, 0.12, it's not in there, 0.34, so it has to be in there. The 25th number is somewhere in that interval. And then what proportion of scores are greater than 80? Probably the easiest thing on there to do is just say, I have 16 values greater than 80. So the proportion would be 0.3, all right, greater than 80. I don't think there's an answer on there. That answer should be 0.32. Even if it's not on there, that's what it is. I have 16 values divided by 50. Okay, so on the next bunch, you can see you have, if you just look at the correlations, there are 3 negative correlations and 1 positive. So the positive correlation is C. So number 4 will be, well, C. I'm not sure why that's not working right now. And I'll just go ahead and say it here. 4 is C. And then going down from there, you can see the A is the closest to the line. So 7, that minus 0.91, 7 is going to be A. And then you can see that the next one where they're close to the line is D. So 6 is going to be D. And number 5 is close to 0, so that's going to be the one that looks the least like a line, and so that's going to be B. Just put this up for a second so you can see the answers on there. Okay, so on the next one, first of all, notice in the responses here that I have two means that are close to 6 and two means that are around 14. And then the standard deviations, you're going to look at how spread out the data are. So the ones in the column over here on the left are the ones that have means around 6. And A is the one that's most spread out. So 8 is going to be A, and 9 is going to be C. And then the two on the right have means around 14 or 13, somewhere around there. And clearly B is the one that's most spread out, so that'll be 11. It has the highest standard deviation. And then D is the one that's left. Okay, so on the matching here, I think that I'm going to get this C first because you can see it's just going to be the one that's most spread out. That's going to be 4C. And then if you look here at A, with the short tails there, you're looking at something that's kind of scrunched in all without much left on the outside, and that's going to look like this because your quartiles are going to be pretty close to the edges on those. So one is going to be A, and then the other, well, it's pretty easy to see here. I've got B and D left and 3 and 4. Well, a couple of things here. A, you can see this one's more spread out with potential outlier here. So 3 is going to go with B. And also, which this is the narrowest, with possible outliers here. And the reason those would be outliers on this graph is because you have so many values piled up in the middle there. So the quartiles are going to be really close to that, and you have a narrow space. So the box, the IQR, is going to be pretty narrow, so it's going to be pretty easy to get 1.5 or 3 IQRs away. On number 16, we have 100 cars, 14 use an alternative fuel. So they either use the fuel or they don't. That's a qualitative variable or categorical, qualitative, and there are only 2 categories. So that's going to be qualitative binomial. I used to always say qualitative and quantitative, and this is an old test. I'll try to remember to say categorical on here. I almost think that's a better way to say it. So we're just putting things into categories. The average number of times that the president says pass this bill, well, I think I know historically when this might have been, is 9.3. So now on the variable on that, quantitative, that's easy enough. Whenever you see average, you have quantitative. But don't be fooled because that has a decimal into thinking that it's continuous. The characteristic of the variable is the variable is number of times, and you can't ask something 1.4 times. You can ask 0 times, 1 times, 2 times, 3 times, 4 times. That is discrete. So be careful about that. That's a common thing for people to miss. They see the decimal on here and they think it's got to be continuous, but that's the average. That's not the variable itself. Okay, so the next 2 are a couple of empirical rule problems. So in the first one, we have a normal distribution. Of course, all the empirical rules will have a normal distribution with a mean of 20 and a standard deviation of 2. And we want to know what proportion of values are below 18. Well, that's one standard deviation. 20 minus 18, and I guess get in the habit of saying minus. That just means we're below the mean. And I'm going to shade in. We want to know below 18. Well, if we're one standard deviation away, we know that this area is 0.34. That's half of the 68. And we know by definition that from the mean down is 0.5. So we'll have to take the 0.34, subtract that from the 0.15, and you'll get 0.16, or C. Okay, we're going to change problem 19. Apparently when I cut and paste, I didn't change the numbers. So let's make that a population mean of 75 and a standard deviation of 5. 97.5th percentile. U is equal to 75. Standard deviation of 5. So we're looking for a point such that 97.5 of the values are below this point, this value of x. Well, again, we know from the mean down is 0.5. That leaves 475 right here. That's half of 95. That means this is 2 standard deviations. So this point is the mean plus 2 standard deviations, or 75 plus 2 times 5 is 85. Okay, we have 4 problems here. Oh, well, that's awesome. 4 numbers there. Since you don't have to show the work, put those in your calculator. I'll figure it out in a minute here. That's actually never shown up there before, but we'll see if it works all right. Put these in your calculator. Use your calculator to get the standard deviation, but realize that it's asking about variance. So when we get our standard deviation, we'll have to square it. So I've got the numbers in there, stat, calc, and tell it whatever list you put it in there. And I get a sample standard deviation of 5.099, about 5.1, but that's not the answer because that's the standard deviation. So take 5.1 and square it, and you'll get about 26. So that's going to be B. In number 21, we have a distribution skewed to the right. So I'll just make this sort of as a histogram. I'll even put something out here. So if you have something skewed to the right, when you compute the mean, the median's going to be, let's say, somewhere around here, whatever that number is. When you compute the mean, you're adding in some really high values. Think back to the example of if you included Bill Gates' income in something. So you have 10 people, the median, the mean might be around $44,000 or something like that. But if you add in one extremely high value, it's going to pull the mean way up, whereas the median will stay the same. So your mean, when you have skewed to the right, is going to be greater than the median. If it was skewed to the left, then it would be lower. For example, if I gave an exam and most people scored in the, let's say, 78, 80, 90 range, but I had someone that scored 11, the median would stay the same, whatever that is, but that's one score of 11 that's going to pull the mean down. Okay, so on number 20, we're into lizards here. Females always mate with males that are 0.75 years younger than they are. What would be the correlation for that? Let me tell you what the most surefire way to get this one right. Just put some numbers in your calculator, like 10, 8, 12, or whatever. Put those in for X or Y, doesn't really make any difference. And then in the other variable, put numbers that are 0.75 less than that. So if you had 8, you would have 7.25. If you had 12, you would have 11.25. And just use your calculator to run the correlation. If you do that, then, well, no matter how you do it, you're going to get a correlation of exactly 1. Of course, you could graph it or something like that. When I worked this morning, I just thought, well, the easiest thing is just to put them in there and put some numbers that meet that, the characteristics of that. And okay, so if the correlation is close to 0, you can conclude that a scatter plot would not have a pattern. So that's going to be B. Okay, so number 24 is another one that just comes out of the OLI text, the online textbook. And let me kind of explain this one a little bit more. I'm going to draw 2 graphs here. One of them would be, let's see, if I had some points like this, and you have a point right here. This point is going to, like if you had a line without that, you might get something like that. But if you added that, it's going to change the slope a bit if you add this point. That's an outlier. If you had that same just main group of points, I know that's not exact, and you had something that was outside the range of your x's by a long way. If you put this into your calculator, into a computer program, here's what the line's going to look like. Even though most of the points look like a positive correlation, that one point is going to be very influential, and it's going to, actually in this case, change the slope and make it a different direction. Especially as we go on through the course and we get more into regression and correlation a little later, and other times with the mean and so on. I would suggest that whenever you do any analysis, that the first thing you do is draw a graph. I can tell you yesterday I was doing a bunch of statistics for a business I'm working with. The first thing I did was draw about 20 box plots. Then I went back and computed the mean and the median and the standard deviation and that kind of thing, because the box plots give you a better picture of what's going on with the data. So anyway, this isn't an influential point right here. And without it, you're going to have probably a slope like this. But if you take that point out, then you're going to have something that increases the estimate of the slope. And again, I'm thinking that's probably a question right out of the OLI. Okay, so for the next one, smokers don't live as long as non-smokers. Heavy smokers don't live as long as light smokers. So you're going to make a regression here. I think the easiest thing on this one is just to draw a graph out and kind of get a sense of it. And so on the x-axis, let's put number of cigarettes or number of packs or whatever. And on the other, we'll put age at death. I don't want to be too morbid, but there it is. So if someone smokes a lot of cigarettes, let's put maybe some ages in here. Let's put this as 40, 60, 80, or something like that. And I'm just going to draw marks there to indicate that I've truncated the axis. If someone smokes a lot of cigarettes, they're going to die at a relatively young age. If you smoke some cigarettes, your age of death is going to be higher. You're going to live longer. And if you don't smoke cigarettes at all, then it might be like that. I know those numbers aren't exact, but that would be the general kind of relationship. And so the slope is going to be negative, and so it's going to be less than 0. Okay, this problem is just 5-number summary, box plot, extreme values, outliers, and so on. So the 5-number summary is going to be the minimum, the first quartile, the median, the third quartile, and the maximum value in the data set. Of course, the maximum is 158, and the minimum is 2. And this is exactly how I'll put it. I'll have 4 columns of numbers, each with the same number of numbers. If you want to do something more complicated, use a computer. So the first quartile is going to be halfway between the 55 and the 65. So it's going to be 60. The median halfway between 68 and 77. That's going to be 72.5. And Q3 halfway between the 79 and the 81, that's 80. So to draw the box plot, I'm going to start with just getting an axis here. Hoping that I leave enough room for this. Okay, so below this, I'm just going to draw a straight box plot without any outliers or extreme values. The box goes from Q1 to Q3, or from 60 to 80. The median is in the middle, 72.5. The maximum value is at 158, and the minimum value is at 2. It looks to me like I should check for outliers and extreme values on both sides. Because remember, the width of the box here, the IQR, if we go 1.5 of those in either direction from the box, then we might have outliers. If we go 3 of those away from the box, then we're going to have extreme values. Could have used a little more space with this. I should have done that first. I've got this one on the board as well. Questions on this one? Of the problems, this one actually gets missed more than the correlation problem. Usually on the correlation problem, I might get some kind of math error here or there. But people tend to, you've worked it enough times, make sure you know the formulas, but most people get that one right. Probably the most common error is someone makes them, and let me say this, if you make a math error on the correlation, you end up with a correlation that's, let's say, greater than 1 or less than -1. If you can't figure it out, use your calculator, first of all, to get the standard deviations and check that. Try and find, and you can use your calculator to check the correlation. You'll have time to do that. I don't think time will be a factor on this test for most people. So check that. But if you just can't find it and you have a correlation of 1.3, right next to that, I know that's wrong. The correlation has to be between -1 and 1. If you have plus 1 point, or if you have 1.3, then I'm just going to mark everything wrong on that problem. However, if you have 1.3 and you say, I know that's not right, then I'll just go find your math error and maybe count off a point. Okay. Did I move too fast on that? Put it right there. I hate that thing.
What is the covariance that you imagine should not do what we calculated with these questions?
Right here. It's the -19 on the top.
Okay.
So
I just thought I had the same bigger line.
the standard deviations were 339 and 3.08. Okay. The covariance will be these cross products. 0 times 4 is 0. Skip it again. -4 times 1 is -4. And it's the sum of the cross products. So it is -19.
Yeah,
Okay, you got that part. And you have to do. So this whole thing up here is the -19.
Yeah.
And then on the next cell, the 19 over the 4.75.
Divided by 4.
Yeah. No, but on the next one, on the correlation.
Mm-hmm. Oh, thank you. Thank you. I got it right on here. Thanks. Copied that wrong down. That -19 should have been -4.75. Sorry. Shouldn't have looked at my paper there. Yes, thank you. That's -4.75, and it does come out to be -0.455. Okay, the next one is interpretation of a box plot. And in the first part, just what is the shape of each box plot, imply about the distribution. So for the BMW3 series, for one thing, you can see that the median is maybe around 32 or 33. I'm going to put 32. And you can see that it's really spread out. It could be anywhere from about 24 to maybe, I'm going to say that's about 67. And you can see by the long tail here that this is going to be skewed to the right. That the BMW 3, maybe that's the less expensive of the cars, and that people maybe can afford that when they're younger. But I'm going to say pretty strong skew to the right. You can also say positive skew. Skew to the positive end of the distribution. For the BMW 5, and I'm not writing in complete sentences here like it says, but I write too big on here. The median is a little bit higher. It's low 40s maybe. I should put approximately. And a little less spread out. It goes from about 35 to maybe 65. Still pretty spread out, but not quite as much. And still some skew, although most of the skew is in this part. You can see that the median is to one side of the distribution. So some skew to the right. You might also note that the median for this group is equal to about the third quartile of the first group. So this median for BMW 5 is about the same as the third quartile for the 3 series. So people are a little bit older when they buy this one. I don't know if that's a matter of price, or maybe it's a little more conservative car. I don't know. I'm not really a car guy. I can't tell. I don't know one car from another, really. I can tell the difference between a pickup and a luxury car and a small car from a big car. That's about it. Or, white versus blue or something. So the BMW 7, the median is a little higher yet. It looks like about 46, and it goes from about 35 to maybe 67. Pretty close in that sense. I'm sorry. Has a higher median than this group. A little bit higher minimum and maximum, but not much. And not as skewed as either of the other two distributions. Slight skew. And that really is one of the main uses of a box plot, whether it's male versus female, trained versus untrained, type of training, type of marketing program, type of advertising or whatever. Putting a box plot and just getting a visual of it, I think is actually a little more understandable than just putting the numbers in a table. Of course, the combination gives you, the numbers are a little more exact, but the visualization is, I think, key to understanding what the data are like. Part B says which group is most likely to have an outlier. Well, it's going to be the BM3W because the tail is a lot longer. And what you'll see is some computer programs will put outliers, some will put outliers in extreme values, and some will just draw out with no outliers or extreme values. But let's see, 1.5 of these would be about there and here. Yeah, there's going to be an outlier in there. Probably not an extreme value, but close. maybe an extreme value. So the BM3W, and you would know because the tail is a lot longer than it is for the other ones. I'm going to go ahead and put it here. Part C asks for the interquartile range for the BMW5 series. So we're going from here to here. It's just the width of the box. It looks like from about 39 to 54. About 15. If you had 14 or 16 or something like that, it's not an exact kind of thing when you're looking at the graph. But in that general area there. Okay, on number 4, random sample of 100 Russellville residents. Average time is 34.6. And we're going to identify all of these things. Surprisingly to me, this actually gets missed more than the problems, historically. Before we get going here, it has average, so we know it's going to be a quantitative variable. Okay? We're going to look at time. Time can have decimals to it. You're not just counting that kind of thing. So that's going to be a continuous variable. So I'm going to go ahead and say quantitative continuous. We're looking at 100 Russellville residents. So that's the sample. I'm going to put SRS, which stands for simple random sample. You can put random sample if you want, of 100 Russellville residents. And if you have the sample, the population is just all Russellville residents. And the element or unit of observation or case is one Russellville resident. The variable is what we're asking of each Russellville resident, and that's how long you've owned your current car. And possible values for that could be 1 year, 17 months, 3.5 days. Of course, you'd want to put all these in the same units before you made any calculations, but I just want to get at the point that it can be anywhere on the scale. Since it's quantitative and continuous, our parameter, and we're looking at averages, if you see average, it's the mean. Parameter is always going to be population, and statistic is going to always be a sample something. Conveniently, parameter and population both begin with the letter P, and statistic and sample with the letter S. And since we're looking at averages, both of those are mean. And the symbol for the population mean is mu, and the symbol for the sample mean is X bar. I haven't covered how to do this one yet, grade point average. I will, but not now. It won't be on this test. So in number 6, again we have a random sample of 100, or we have a random sample of 100 students enrolled in BUAD 2053. So that is our sample. I'll put SRS, simple random sample of 100 students in BUAD 2053. So the population will be all students enrolled in BUAD 2053, and the element or case will be one student in BUAD 2053. The variable is just whether or not they used R in the assignment. That's a qualitative variable, two categories. So whether or not I'll just put whether or not they used R. That is a qualitative or categorical variable with two categories, so that's a binomial. And the possible values are yes or no, or you could put used R, didn't use R. And since it's a categorical variable, we're not computing averages, we're just computing proportions or percentages. In stats, we usually talk about proportion. So the parameter is the population proportion, which is P, and the statistic is the sample proportion, which is P hat.